Hi everyone, I think we're gonna get started right about now. Um, Welcome, thanks for coming. And yeah, we'll get into like introductions on the next slide, but basically like we're just gonna explain like a lot of what it looks like to be like in astronomy, especially as an undergrad. Like what are the classes you'd be taking, like what are the like different fields within astronomy, like what research looks like. So we're just gonna get right into it.
Hey guys, I'm Josiah. I'm currently a senior at University of Michigan, and I'm studying stellar halos and galaxies for my research.
Hello, everyone. I'm Andrew. I'm also a senior, and I am currently studying galaxy clusters and black holes for my research.
I'm Chris, I'm a sophomore, and I'm studying binary populations in the Orion Nebula cluster.
And hi, I'm Anna. I'm a junior studying physics and astronomy, and my research interest is primarily in planetary science, particularly the Kuiper Belt and Jupiter-Trojan asteroids.
So to start out, we're just gonna go over like certain skills that you can start developing even now as high schoolers. For math, like ideally, like you have some sort of experience or in calculus and maybe in statistics. If you don't, like that's fine. You can just take those courses in college, but having that sort of background is definitely beneficial, seeing as you know physics is obviously a very math intensive field. Within physics, again, ideally you've taken mechanics at the very least. I know a lot of people don't have an opportunity to, you know, take like electricity and magnetism or like physics classes beyond that. I personally didn't have the opportunity, but just having even mechanics background is really important. Physics, obviously, if you're studying astrophysics, is really important. In terms of astronomy itself, you know, typically most high schools, I would say, don't offer full-fledged astronomy courses. Um, but there's, you know, things you can do on your own. In terms of observing, I would say, you know, for this picture on the right, it shows like a coordinate system on the sky. You don't have to know like all the specific coordinate systems like quite yet, but I think it is useful to start getting to know just how we know where things are in the sky and just have a general idea of where some of like the most major stars are in the sky. Um, Even if you're more like interested in some of the like the more physicsy aspects of like you know studying stuff like black holes, at the end of the day, like how astronomers get our data is we look at the sky, and so being able to understand.
Uh-oh, I think Chris may have lost connection with us a little bit. We'll just give him a couple of seconds there to reboot, and we should be all good. All right, unfortunately, I think we might just have to finish up Chris's slide for him and move on, but we can get back to this because I know Chris had some really cool thoughts he was going to share with you guys. But just to kind of wrap up on this slide, oh no, it looks like he got kicked out of the meeting. Just to give some background more on kind of what he was saying, you need to know where things are on the sky, and there's this whole set of like three-dimensional celestial coordinate systems that we use in astronomy that you might calibrate your different instruments and telescopes to, and being able to understand not only where an object is in the night sky at a certain time, but also where it's going, how fast it's moving, you know, how much of the atmosphere is going to be getting in the way if it's directly overhead versus off to the side, are actually a lot of really important things that astronomers who observe think about every day that you might not necessarily consider. And of course, Python is also a really important thing to have as well. Chris, are you back with us?
Yeah, my internet
Perfect.
is a little shoddy right
All
now.
right, Chris, I will pass it on to you to just finish up your thoughts on the slides. Sorry, we had to just make sure that the show could go on, but I'm glad to see you're back.
Are you serious? Oh, sorry. Did you guys get my whole just like on the background knowledge part, or was that completely cut out?
We got it. You just cut out when you were talking about looking up things in the sky.
Oh yeah. So my okay, my point on background knowledge, um, is that like that does not mean like reading astronomy textbooks. necessarily. That can even just mean like looking at YouTube videos, reading Wikipedia, like reading like news articles of what's going on in, research in astronomy. Just sort of have that sort of having that baseline knowledge is like can never hurt. And then for coding, yeah, like obviously everyone varies in their experience with that, and you don't need to have like tons of coding experience before you come in, but if you can get your hands on some coding experience, especially with Python, that is very beneficial. Your research is essentially going to be 70% coding. So that's, yeah, that's an essential skill if you're doing research in astronomy.
Yeah, so now we'll move kind of into the big branches or different sects of astronomy. And so some of the bigger, more overarching themes are cosmology, which is the study of the universe as a whole, galaxies, planets, stars, high energy physics, and then instrumentation. Instrumentation specifically is that would involve telescopes, detectors that are attached to telescopes, observatories, anything of the like, and computational, as has been mentioned before. Coding is a very big part of astronomy and astronomy research. And so some astronomers and astrophysicists do work specifically with only computational work, which would involve maybe doing galaxy merger simulations and anything of the like. One thing on here that I want to make a distinction of as well, as for any of these categories, cosmology, galaxies, planets, you can be either a computational version of that or a observational version of that. So for most any sect of astronomical research, there are the people that are putting together the telescopes, that are out actually at the observatory, taking the measurements, collecting the data, storing the data, anything of the like. And then there's a sect of people that are taking that data that has been collected and then are analyzing it, scrubbing it clean, and working with it in order to get results that will then be published into papers. And so we'll move on and we'll go into each one of these branches into more detail. And so first is cosmology. As I said before, cosmology is the study of the origin and evolution of the universe. This covers topics including Big Bang and inflation, the cosmic microwave background, large-scale structure, which is imaged in the back, and the composition of the universe, including things like dark matter and dark energy. If you were to do research in cosmology, some things that you might encounter are examining expansion of the universe with supernova data, mapping the blueprint of the universe with a Chilean telescope, that blueprint being the cosmic microwave background, and processing galaxy cluster simulations to aid observers in the work that they do.
All right, so galaxies. I'm sure you guys have probably maybe even seen this picture before, heard about what a galaxy is. I mean, obviously, we live in a galaxy, the Milky Way. They're kind of these huge cosmic bodies that are these amorphous collections of stars and all sorts of other matter. So what might you be actually doing if you're researching galaxies? And I think that the way that Andrew broke this down earlier, that there's this observational side and this computational side is really just right on. So I would even say that there's almost three stages. There's the people that are really into the instrumentation that maybe are actually like doing the observations. So in the case of my research, a long time ago, a professor in the department had a proposal of a research study, and he applied for a grant with the Hubble Space Telescope. The Hubble actually did the observations as he specified in his grant, and then we got the data. And we've been working on that data for years. And that's kind of that stage two, where you're taking the data, you're putting it in Python, you're cleaning the data, maybe you're graphing different things in the data, you're running different statistical analysis to see if the things you're observing really have any significance, or if it's possible they're just noise. And you're kind of doing all the data-oriented stuff, which is still observational. But then there's this other portion that works really well with it, which is computational astrophysics. And that works very, very hand in hand with galaxies. So in the case of the work I'm doing, once again, with this Hubble Space Telescope survey, we have this data, we've cleaned this data. What are we exactly trying to show with the data? One of the things we're trying to show is we have all these stars that we know are in this galaxy, and we can graph them. We can graph that, we know these stars are red and these stars are more blue and all these other things. What does computational simulation tell us about that? If somebody else who was a computational astrophysicist who was working on galaxies ran a huge simulation on a supercomputer, and they had kind of this result of where they thought the red star should be and the blue star should be, is that what we actually observe in the galaxy? And that's where really good papers come from, where you're informed by not only all the other observations that have been made on the subject, but also the computational aspect and what our models can predict. And the reason this is useful is if you find a contradictory result, something with that model isn't right. And this is how these models get developed and refined over time. But if you find something that's exactly in line with that model, then this is a really, really cool confirmation of some of the theoretical work that's being done there. So I just wanted to emphasize that. So going back to galaxies, what are things that we learn about galaxies through research? I kind of talked about how there's this observational side, this computational side. There's just three things I want to bring it down to that at least I have encountered in different classes or in research. First one is dark matter. That's a whole topic. If you ask us what it is, we don't know. Scientists actually don't know what dark matter is. That's kind of how it's got its name. But basically, we've observed strange gravitational phenomenon that can't be explained without some sort of a large invisible mass influencing objects. And happy to talk about them more in Q&A, but they're especially specific to very large groups of astronomical bodies, such as galaxies or galaxy clusters. That's where you observe their effects best. And dark matter distributions is something that's a hot topic in galaxies for sure. I already mentioned distributions of star populations. It can be confirmed through the computational. It can contradict. Really important stuff, really interesting, kind of what I'm working on. And then here's another one, the mechanisms and timescales of mergers. Galaxies actually crash into each other a lot, very often. In fact, the galaxy in this picture has a galaxy that's kind of passing under it, and it's stretching out the spiral arms of that galaxy. And the Milky Way and Andromeda are actually supposed to collide at one point. Many galaxies that are larger have already collided with many galaxies over their lifetime. So through using some of these methods based on these simulations, if we find observationally info that matches the simulations, where the simulation showed a galaxy colliding, then maybe we can start to infer when did the last galaxy collide with this galaxy? Was it a billion years ago? That sort of thing. What was that galaxy made of? How much iron did it have in it? Those sorts of questions. And these are all things that you can answer in galaxy research. And I know I've kind of been going on a while, so I'm kind of wrap it up here. What are things that you actually do in galaxy research, and why might you need Python? One is a rotation curve. This cool galaxy with this spiral arm is actually rotating, right? It's actually moving around. So if you look at a galaxy edge on, like you look at a Milky Way, where it's kind of like this disk, you can measure how quickly it's rotating based on measuring the color change in stars that are coming towards you versus stars that are going away from you. It's much more complicated than that. It uses a lot of trigonometry that's not fun to calculate, but you can use that to figure out how fast a galaxy is rotating. Density profiles, I already mentioned. This is just, if I have a clump of red stars that are kind of making this shape in one part of the galaxy, how can I statistically measure how big that clump is? And what does that say compared to these simulations, which is the third point. So I just want to emphasize those are some reasons that we research galaxies. That's what we can figure out, and it can inform simulations and other observational data. And of course, those are some specific things you might be doing with Python, with other coding languages as it pertains to galaxies research.
All right, so the next overarching topic, and this is the topic that is my main research interest, is planets. So planetary science is the study of the planets in our solar system. So obviously we have our 8 actual planets in our solar system, but also basically any rocky or gaseous body that orbits our sun. So this includes the asteroids, comets that may come into our solar system, the Kuiper belt, the moons of all of the planets, and basically anything else in the solar system. And some would also include the study of exoplanets in this. So I'm just going to include them here to touch on that because that is also a very hot area of research right now. So the main questions that are being looked to be answered here is basically, how did our solar system become the way that it is today? How did it form? How did it evolve? What kind of objects does it contain? Can we find more of them? So in planetary science or study of planets, at least on the solar system scale, you're doing observations of various objects to determine their composition, to find out, and also to find out if there's new objects out there, determine what their orbit is. And hopefully new observations can lead to new information which can inform our answers to these questions about how the solar system evolved and what materials are contained in it, and what can those materials say about where these different objects came from. So of course there is the observational side where you are taking data from a telescope and analyzing it. There's also a more computational side, as Andrew mentioned earlier, and this can include simulations of solar system dynamics to figure out how the orbits of planets have evolved over time and how that affected orbits of other objects. So this is kind of the big question is what changes happened in the early solar system that led to it being the way it is today. And maybe an example of these computer simulations in action is the search for the proposed hypothesized Planet 9. So looking at the orbits of Kuiper Belt objects, is there an explanation for why these orbits are the way they are? And can we simulate that using a computer to see if you have evidence to support that theory? So that's kind of one example. So here are some other research examples I put on the slide, and these are things that I do personally. So one of them is identifying new Kuiper Belt objects in survey data. So basically, the data are just large areas of the sky. Well, not that large compared to the whole sky, but you have quite a bit of space. You're not like focused in on one little object. You're getting a larger area of the sky, and you have lots of data over various nights. And you're trying to find these new Kuiper Belt objects in this data. And while stars will stay stationary for the whole night, the whole time you're taking the data, the Kuiper Belt objects will move. So you want to find these moving objects, and then you want to determine their speeds in the sky. So how much distance are they going to travel in a certain amount of time? Because this can help you recover those objects eventually with further observations. And the more observations you have, you can actually characterize the orbit of them. And then that's helpful for understanding the overall evolution of the solar system. And then another example is just using radio wavelength data and thermal modeling to look for possible evidence of ice on Jupiter Trojan asteroids. So this is another project of mine, and basically this is kind of different because you're observing very specific objects and you're looking at them and you're getting this radio wavelength data from them. And then from here you can get clues in terms of, you can find out its diameter and albedo by using these models based on this data. And then from that, you can use the albedos to determine if maybe there's ice on them, which would be really cool to understand what they're composed of, and possibly find targets for further observation to help answer some of these questions of how the solar system formed and how these objects all relate to one another in the grand scheme of solar system formation. So it's a very cool field, very interdisciplinary, because you have a lot of different things involved. So you have physics in the terms of dynamics, and I mean, physics is everywhere, but there's also, chemistry. You're looking at spectra of objects, so understanding chemistry and chemical properties can be important here. You can also look at like the geology of different moons. So there's really a large variety of things to study in this field, which is why it interests me a lot.
Yeah, so obviously I think one of the first things that comes to mind when people think of astronomy are stars, because they tend to be the brightest thing in the sky outside of the planets we can see in our own solar system. And because of this, they have always been some of the best and easiest targets to research, just because they emit the most light, and light is sort of how we observe up until like the discovery of gravitational waves. Electromagnetic waves were pretty much how we know everything we know about the universe. So some example questions that pop up in stellar physics is like, how do stars form? And obviously there's a lot of knowledge about how that sort of process already occurs in terms of hydrogen gas cloud collapsing onto himself, but there's a lot of specifics and details. It's not just simple as you just get a bunch of hydrogen together. And so like obviously there's a lot of research that is being done there, especially in what are nebulas, which are essentially star nurseries. That's where stars are born. And we can observe many. And so those are hotspots for observing star formation. Also like learning about stars' properties. So that includes like its temperature, its size, its metallicity, the sort of wavelengths of light it gives off, those all tell us different things about stars, and we've observed patterns about, so let's say like a star is a certain size, from that we can infer its temperature, from that we can infer its spectral type. And so scientists have already determined a lot of the different patterns that we see in like the different types of stars, but again, that's still something that's obviously being researched. How do stars move and interact with each other on a grander scale? That arguably goes into galaxy domain, but obviously stars are not stationary. They're constantly moving, and like we can observe how stars move based off whether their light is red shifted or blue shifted. Again, and then what happens to stars when they die, and how do those processes actually operate? So again, we have a working theory that's about, stars can either turn into a white dwarf, a neutron star, or a black hole. But again, how those sort of processes actually occur, how do supernova actually, how does like a star actually generate that much power to, explode in the way that that, because supernova have ridiculous amounts of energy, and the sort of exact process that leads to that we're still not entirely sure. And so obviously, again, a very active area of research. In terms of what you may encounter, personally, what I'm doing is looking at binary systems of stars. So stars that orbit each other, you could have 2, potentially 3, 4 stars that are gravitationally bound to each other. And so what I personally do is, because those 2 stars are orbiting each other, they're going to be often too close to each other to, separately resolve them. When you look at them in an image, it's just going to look like one big blob. And so you can make a fit to that using statistical and computational methods, and look at it's a lot of statistics to determine whether, like, what is the percent probability that this is a binary versus just a single star. So that's what I'm doing. Profile fitting to targets whether binaries or not is very common in stellar research. From there, you can look at stellar population statistics, like what percent of stars are this spectral type, what percent of stars are binaries, what percent of stars contain this element in them. And obviously this can, tell you something about a certain population of stars. And going along with that, you can, what you might be doing is interpreting stellar spectra, because that can tell you not just the temperature of the star, but also like what elements are contained within that star. And this is also this is also the same way that we find out what the atmospheric components of exoplanets are. So there's a lot of like different things you can do and look at with stars.
All right, so the next branch of astronomy that we'll mention is high energy astrophysics, and this is the study of kind of the extreme instances of the universe. And so this includes compact objects. These are things such as white dwarfs, neutron stars, black holes, so anything post-stellar death. This is a good connection to stars, in which we have just talked about, and can be applied to any of the previous branches that we've talked about. There are always extreme processes that are happening, whether it be at the cores of galaxies, in between galaxy clusters, or at the beginning of the universe. Specifically for cores of galaxies are quasars and active galactic nuclei. On top of these larger scales, these larger structures such as like stars, black holes, galaxies, this also includes things such as neutrinos and cosmic rays. Cosmic rays are high energy protons or helium nuclei that are emitted from astronomical objects such as active galactic nuclei, and neutrinos are what we thought to be massless particles, but are particles that are very difficult to detect, that are emitted from high energy events such as supernovae and the like. One thing that I'd like to mention that Chris had touched on was that light for the longest time has been the great messenger of the universe. That is how we've been able to learn about what is out there. But that has changed in recent years, as back in 2015, through LIGO, we were able to detect gravitational waves. Neutrinos are another way in which we have been able to detect things. We use Cherenkov detectors. Specifically, there's a large one in Antarctica called IceCube, in which neutrinos and other high energy particles are detected. And this there is a, I guess, subclass of astronomy called multi-messenger astronomy, where if you have one source, such as a neutron star merger, you're able to get electromagnetic information from it, gravitational wave information from it, and perhaps even neutrino or cosmic rays information. And that is a new frontier in astronomy. There's a lot of money getting put into that. So look out for multi-messenger astronomy in the future. There's a lot that will come from that. On top of that are things such as shocks, relativistic jets, and high frequency emission. Shocks just mean if you have, say, a supernova goes off, the stellar winds from that, when it pushes that material out, are going to smack into the material that is already in the interstellar medium and create a shock front. And so that is an area of study that people are looking into. Relativistic jets, say you have a black hole with an accretion disk around it. Oftentimes the material that is accreted around will get spit back out in these big relativistic jets. So that's another very exciting field of study. And then there are multiple particle processes that give us high frequency emission, which would be anything X-ray, gamma ray, that we are able to detect. And then as I mentioned before, gravitational waves could potentially be grouped into this as well. So if you were to decide to do research or wanted to do research in a high energy field, some of the things you could expect to do would be to fit models to probe the origins of supermassive black holes, measuring faster than light particles in the Antarctic ice. That's what I had mentioned before. Kind of what happens is as photons move through the Antarctic ice, they slow down relative to their speed in a vacuum. However, a particle like a neutrino or another lighter particle is not as deterred by this Antarctic ice. So in the medium of the Antarctic ice, those particles move faster than the photon itself, and it causes a light version of a sonic boom, which is known as Cherenkov radiation, and we are able to detect that and rebuild these particle interactions to detect sources in which they may have come from. Another thing that would fall into this is you could simulate orbiting bodies such as black hole neutron star, or neutron star in order to probe the behavior of their dynamics as they're orbiting each other. How long does it take for them to infall? What kind of radiation are they giving out? There is really a lot of exciting stuff happening in high energy astrophysics.
All right, guys. Now you might be wondering, that's a lot of jargon. That was a lot of information we threw at you. How on earth can you get started? We've already seen some great questions in the chat. So just to break this down, I really wanted to emphasize that a lot of you had great questions about, matplotlib and numpy and scipy and all of that. And there's all these other libraries in Python as well, such as astropy. And if you guys don't have any idea what I'm talking about, there are no worries at all. There's two really great resources for Python. So one, how do you start coding? What if you don't want to download a bunch of Anaconda Python stuff in your computer? You don't know how to use the terminal. That stuff can definitely create some barriers. So what I do, and what some people, and even some some people in my research group do, is they use their Google accounts. So if any of you guys have Google Drive, if you can use Google Docs, Google Slides, anything like that, this PowerPoint is made on Google Slides. You can access something called Google Collaboratories. So when you go to your different apps, you can go to additional apps, or I don't know what the exact tab is called, but there's this symbol, this orange kind of infinity sign down here at the bottom of the slide, which stands for Google Collaboratories. And you can go to Google Collaboratories and it will open what's called a Python notebook, which means that you can code in different modules in different boxes, and you can code those individual ones. So that's super, super helpful. If you want to get started with coding, highly recommend that. Happy to answer questions, maybe even share a screen and show you how you can get started after this during Q&A. Also, for learning how to code, if you ever run into a problem, Stack Overflow has answers to just about everything, including people who've worked with different astronomy libraries such as Astropy. I go there all the time. Also, Astrobytes. I think actually, Anna, could you speak to Astrobytes a little bit? I think you actually use this more than I do.
Yeah, so Astrobytes is a great website that posts accessible summaries of recent astronomy papers. So for the most part, they're written by grad students, and they're really great ways to just kind of get to know some of the research that's going on, see what sort of things interest you, because academic papers can be really hard and intimidating to read, especially if you don't have any experience with that before. But the Astrobites articles and summaries are a lot more accessible and manageable to really understand what's going on. So I highly recommend that to get a feel for what astronomy research is currently happening and to see what sort of things interest you that you might want to do research in the future. I think you'll probably find it a lot more fulfilling than just going and reading random papers. But Astrobites also does link to the papers that they write about. So if you do want to dive in and see what an actual research paper looks like, definitely recommend that. But don't be turned off by the difficulty of reading them. Because, you know, I still have issues sometimes parsing what real academic papers say, but I think Astrobites is a great way to really start getting into that and to learn about different areas of research.
Absolutely. Thank you for that, Anna. And to that end, you know, Astrobites links you to papers. If you ever just want to go full out and just read some papers, which, you know, is really tough, but sometimes we have to do that at the collegiate level when we're preparing research. We have to know like other papers that were precedent that might affect what our findings are. Then a great place to find those papers is the Astrophysics data system, just ADS. Typically, if you find any paper, it's going to be here. And the citations have links, so it will link you to other papers that have been referenced. Just a little bit of advice on reading papers. They're going to be divided up into a lot of sections, like an abstract, an introduction, a method section, discussion. There's a lot going on there, and it's not fun to read if you don't really know what you're doing. So what I would recommend, if you decide to go to ADS, just read some abstracts and see if the general topic is interesting. If it is, maybe look at one or two of the graphs and just try to figure out what's going on. Sometimes a summary or discussion section can also be helpful, but if you're just trying to get an intuition, reading everything is not necessary at all. So just want to encourage you guys there.
All right, so lastly, I'm just going to talk about the classes you might encounter in college and need to take as part of a degree in astronomy or astrophysics. So obviously math is really the foundation of understanding physics, so you're going to want to have a strong foundation in that. Usually at Michigan, for example, you have to take multivariable calculus and differential equations, but that can vary depending on where you pursue your degree. We also recommend knowledge of statistics. It's really helpful when working with data. So even if you're not required to take it, if you get the chance to, definitely do so, because it's super helpful when interpreting data and knowing what to do to understand the statistically correct way of doing things. Second, physics, obviously very important. So you can expect to take like advanced mechanics and E&M, which are more mathematically intensive than something you might take as a high schooler or a freshman in college. You also may consider taking quantum mechanics, optics, or thermodynamics. If you decide to pursue, say, like a double degree or a double major in astronomy and physics, you'll most likely have to take something like quantum mechanics, thermodynamics, although these requirements can vary from program to program. And then lastly, of course, you're going to have to take astronomy classes. That goes without saying. So the sorts of things you might study in these classes are stellar physics, galaxies, observational techniques. Here at Michigan, we have elective courses on exoplanets and computational physics. You could possibly take a course on instrumentation. A lot of these sorts of classes vary, again, from school to school. So this isn't the exact thing that you would find at whatever university you end up attending. But this is sort of an overview of the sorts of things that you are likely to encounter in your studies in college. All right, so that about wraps up our presentation. We really hope that you enjoyed it, you learned something. We are here to answer your questions now, so if you have any questions or comments or wondering about something, please let us know and we will do our best to answer those.
All right, and just really quick, Chris, is it all right if I stop recording now just so we can kind of have like an open Q&A?
I mean, I think people like not coming to the meeting would appreciate hearing the questions, right? So
Okay, sounds good. I'll go ahead and keep it recording.
Okay, I could just like start with some things that are being asked I'm seeing in the chat. So one is like if number theory, topology, or pure math helps. So obviously, if you're going to look at more kind of the theoretical physics topics, kind of where that intersects with astronomy, that's going to be more helpful for understanding things like general relativity. Basically, the more theoretical you get, the more pure math helps you. I mean, I'm only an undergrad, so I don't know the whole everything that is involved. I don't know every step involved with every part of observational physics, astronomy. But in my experience, I really have not used very theoretical math at all. So a lot of things have been more applied, like understanding statistics and statistical implications of what you're doing, understanding like the physics needed. But yeah, that's kind of what I've encountered. But if you're interested in more theoretical things, more math is never going to hurt you. So really pursuing math as much as it interests you, I would never recommend somebody not do that.
Yeah, with regards to the questions about the observatory, so Michigan does have a quite like decently sizable telescope, but and even though it is professional grade, we don't actually use that we don't use the data we take from that to do research. Like there's plenty of databases out there that like have that like that already have usually all the data we need, and because applying to use a telescope for your own data is an extensive process and not something you would really be doing as an undergraduate, at least that I know. So typically, like, yeah, it's always going to be remote observatories, and usually like you'll have you probably won't be taking the data directly, just because again, like it's a very very extensive application process.
I just want to piggyback on that too really quick. So another reason that our telescope, even though it's professional grade, isn't used as much is the city of Ann Arbor is a horrible place to make astrophysics observations because there's so much light pollution and the weather is usually not very good. Places that maybe are in a mountain in Arizona or maybe that are in Chile or other places are better candidates. And I think Andrew could speak to this more, but we have kind of a sister observatory in Kitt Peak, Arizona, that we sometimes send people to for a class, and there are observations that come from there. Another one in Chile as well. And once again, like Chris said, like there's a lot of data that's either already out there or that maybe you have in a department because a professor applied for it. And once again, like the Hubble telescope data I'm working with is there not because it was in the public domain, but because a professor applied for it years ago. And now we have it sitting around in that research group. And that's a great opportunity about going to a university, wherever you decide to go. The different types of areas that they focus in might mean that they have different exclusive types of data based on what types of proposals those professors have written to observe on different telescopes. So just want to throw that out there.
Right. I think the big takeaway from that is that telescopes and observatories in general are very expensive things to put together. So oftentimes collaborations of several universities and other institutes come together to fund these projects. And so they're often in locations that are away, either in space or in mountaintops for optimal observational conditions. And then that data either goes to the institutions that are a part of it, and then there's some moratorium time on that, and then most likely data then will become used to the public. That's not always the case, but that's sometimes true.
I suppose I can start explaining a little bit more extra plans if you're just curious about that. So like I think by far the biggest method that's currently used is transits, which is where an exoplanet will like essentially block part of its host star, and so we can detect a literal drop in light from that star. And if that pattern is cyclical, we can then infer that there's a planet orbiting it. There's also other methods involving that have seen very little. Some of these methods actually have seen almost no success because our instruments don't have the precision to detect them. But one of them might be detecting the star's wobble, because when a planet orbits around its star, the star is actually affected gravitationally and will, move a bit. Like our own sun moves a bit, mainly because of Jupiter. And so you can detect the sort of shift in that star's, in the type of light that it emits. Again, seen very limited success because that sort of shift is very subtle. That's sort of another way that we can detect them if someone wants to continue where I left off.
Chris, I think you kind of hit the nail on the head there. I'm not really an expert on exoplanets or anything like that. So anyone else who has experience, feel free to chime in. But
Yeah, good explanation, Chris. I'm going to go completely off brand when it comes to planet topics, since that's not my area of expertise, but you seem to know just as much as I do. So
I mean, I guess another thing that's really cool that we can do is we can get some knowledge about the atmosphere composition of certain exoplanets by looking at, because when an exoplanet transits its star, the light will go through that planet's atmosphere. And so the light there's sort of these like elemental signatures that are, sort of printed onto that light that we can detect. So I would say for exoplanets, the most amount of knowledge we can get about them is its size, its mass, its distance from its host star, and maybe its atmospheric composition. Other than that, like it's still very much a very exciting but pretty developing field. And so if you've ever seen like a sort of like quote unquote picture of an exoplanet, it's just an artistic depiction. We don't actually have any high quality images of exoplanets like that.
we have a question here about SQL. I put a little explanation there, but I think Andrew actually has experience working with it. So Andrew, if you want to answer that question, I think that'd be some really useful information for us.
Yeah, so SQL's I don't I hesitate to call it a coding language, but it is a set of specific commands that you can use in order to parse through a data set in order to get things that you want. So specifically, if you're working with something like the Gaia data set in order to get information on stars in the galaxy, you can use SQL commands in order to get a specific criteria of data from that. So if I wanted stars that were brighter than 13 magnitudes, that were within 5 parsecs, that in the G and R band magnitudes or whatever different specifications that you would want, you would use the SQL format in order to pull from the data set as a whole. For something like Gaia, that's terabytes in size, your computer could never handle having all of it on one machine. And so you use SQL in order to pull specifically what you want into a data set that's much more workable.
That's a really good explanation, Andrew. Another thing about SQL is you can access it through the terminal on your computer. If any of you don't know what that is, that's totally okay. But it's basically this this like command line where you could just go on your Mac if you have a Mac and search command line or terminal. This little black box will pop up with what looks like what you see as someone who's coding in the movies saying, "I'm in, guys." It's basically has all these commands that you can do to access different things in your computer. You can use that to run SQL commands.
Yeah, as like on top of, I know we've mentioned Python a lot. Another good coding, I guess, area of knowledge to have some like knowledge on is called Bash, which stands for Born Again Shell. And so it's just the commands that you use in a terminal in order to work your way through files, how to move things to different places. It's a way to work with data, move things around rather than physically like clicking and moving things. You can just use a couple commands in order to move data where you want it. It's a little bit of a steep learning curve at first, but once you get the hang of it, it's a very useful tool in order to sort and arrange your data.
Also to answer the question about if we work on our own laptop doing research projects. So personally, for my group, we have a remote computer that most of our data and stuff is stored on, and the specs on that computer far outweigh those on mine. So doing more computationally intensive things are usually done on a remote computer to run code, but usually, for most general purpose, just code writing and testing, I can do it on my own laptop, and that seems to be the case for a lot of people too.
Yeah, just really quick before we get to the next question, to piggyback off of what everyone's been saying about other computers, is you might be wondering, why do I need to use a remote computer if I could just run code on my laptop? Like I could use Google Collaboratories, right? And the answer is sometimes you might have a function that works perfectly well and is as efficient as it can be, but still takes 15 minutes to even print out a graph. And when you have code like that that takes 2 hours to print out a graph, and then it has to print out several graphs, or maybe has to run a simulation that takes a day to run, then because of that, there's a need to have supercomputers or computers with higher specs, and also computers that won't crash when you're trying to run all these different commands or functions, because of course, if it crashes in the middle of running, then you might lose a lot of progress that you did want to lose. I think regarding the question on everybody's biggest challenge in astronomy, that'd be great if all four of us answered that. So I'll start. My biggest challenge has been bugs in the code, just like when data doesn't work and it should be working. So one of the things that I've had to do is make a set of functions that are kind of set up to deal with the data set I'm working with. So again, what I'm trying to do is I'm trying to map out the types of stars, like, old stars versus young stars, what masses, what age in their life cycle, that sort of thing, and where they're distributed across the stellar halo, which extends very far beyond the disk of this galaxy. And in order to do that, one of the things I have to do is plot the density of, how many light years squared basically per star am I measuring? And, sometimes finding that area, how many light years squared, is more complicated than you think, because instead of doing it, in terms of geometry, you have to do it in terms of the pixels on the camera that's being used. And that can become very complicated. Running through all of the pixels in the camera is not feasible. So trying to decide, what's the most efficient number of pixels to actually index through, how do I compensate for error? How do I even calculate error on those sorts of things? Those have been my biggest challenges thus far in astronomy.
Yeah, so I can kind of say mine. So personally, yeah, there's a lot of issues to be found with coding, and it's often very frustrating to track down these issues. But also, part of the challenge in doing research, but also kind of part of the reason why it's a fulfilling thing to do, is really just kind of determining what steps you need to take to get to your goal. So if you have some objective you want to do, like, for example, I want to be able to find the speed of an object that we found in survey data. That's not really a straightforward thing to do, because all you have are a bunch of images of this object or of the sky that contains this object over a certain period of time. So it's really kind of the problem solving aspect and identifying what the useful thing to do here is, what the thing that makes sense here to do is, and just figuring out what you need to implement to get to your goal. But once you figure that out, it's very great to finally see results from that. So I'd say that that's kind of the big challenge that I personally find both challenging and rewarding in doing astronomy research. Yeah.
Yeah, I'll chime in next. Definitely going off of Josiah and Anna, I've definitely also had my run-ins with coding bugs. That is one of the biggest things, is wondering kind of what's getting in the way and making sure I'm parsing through and looking at every line to make sure that everything is working in the way that I want to, and making sure that I am speaking with my advisor and getting the help that I need. But I guess one of the more exciting challenges that I've run into was over the summer. I had the opportunity to present at our collaboration meeting. It would have been in Spain, but COVID had other plans. But I was one of the few undergrads that presented at this, and so putting together a presentation, kind of collating everything that I had done and making sure that it was professional and up to par of the presentation was a really rewarding experience. I was very proud of what I was able to do. Yeah, so that was one of the more exciting and fun and rewarding things that I've been able to do through astronomy. Getting to present some of your results and show that, like, this is what I've been able to produce, I've been able to contribute to science, is a really cool feeling.
Yeah, I enjoy my research, but I don't, I don't think this comes as very exciting. But in terms of something that is like, I would say universally a problem in a sort of like challenge or hurdle that sort of astronomers have to deal with in general is noise in their image and getting rid of said noise. Because, when the telescopes take, images and there's a lot of other, like, what is frankly junk that gets onto the images. And being able to sort of parse that from like what you actually want to observe is an entire process that you become very familiar with, and I think I've become much more familiar with, but um it it can be quite a challenge to like just deal with that kind of stuff. And pretty much no matter what you yeah, whenever you take data in like pretty much any scientific field, like there's going to be a lot of extraneous factors that will get in your way. And you just have to find ways to get rid of them. So
All right, so a while back there was a question about university summer programs about astrophysics, and also like impact of COVID-19 on research. So I can kind of quickly go over like possible summer programs, at least in American universities that I know of. So there's a great thing here called RUs, which are research experiences for undergraduates, that a lot of different universities host across the US every year. Unfortunately, those require US citizenship in most cases. I don't know how much that applies to everyone in this presentation or not, but just throwing that out there. There are other programs that don't though. So I know, for example, there's like the surf program at Caltech that welcomes visiting students. So there's one for like LIGO, for instance, and those don't have a citizenship requirement, but yeah, there's really a lot of different summer programs to do once you get to university. I don't know if this is like asking for things to do once you get to college or while in high school, but these are the ones. I'm not familiar with any in high school. I never did that, but these are the ones you could look at once you get to college. So typically like applications for those are usually due around like January, February, and then you'd go for usually like 10 to 12 weeks in the summer to work on a research project. So that's kind of the overview of that. I actually did a summer program remote this year because of COVID-19, and just to personally touch on that experience, I still had a great experience. It would have been great to go in person and meet everyone. It's very strange that I feel, I've made connections with people in my research group and I've literally never met them, which is very weird. But if you have an advisor that's really open with communication and you're making sure to check in with them a lot and communicating your difficulties, I think that if you're not doing lab work, where obviously that's going to be an issue, research in astronomy can still be done remotely right now. So that's just been my experience.
yeah, you can, considering most astronomy is done just like coding, I've been able to continue my research, and we do our weekly Zoom meetings. So thankfully, like especially compared to like other scientific fields, like it hasn't impeded as any, or like it had, like obviously it doesn't help, but we're still able to continue things on to an extent.
All right, I can also like answer Michelle's question. Searching for Kuiper belt objects. Okay, so I don't really know what method of Laplace is. Like I've never really encountered that before, or maybe I have and just don't know I have. But I can tell you kind of what we do to find Kuiper belt objects. So like I said, you have a bunch of images of the sky taken over a certain period of time. So you've taken them over, maybe the course of 2 hours or something in a night. So you have all these different exposures. So in these exposures, stars are going to stay stationary, but real Kuiper belt objects are going to move very slightly. So of course, you can do things like subtract out the stars. So your only sources, if all things go well, are just your transient objects, so objects that move in the sky. That doesn't always go great because, subtracting out these stars can introduce different image processing artifacts and like what Chris earlier called junk, which is very accurate, into your images. but that can also help eliminate the number of things you have to look at. But then you can also basically stack all of these exposures on top of each other. And so this increases, basically it increases the brightness, how bright things appear in your images of each object, so making it easier to find fainter objects. But instead of just stacking them all on top of each other, you can also like slightly shift each successive exposure at a certain rate. So you kind of know just vaguely how Kuiper Belt objects tend to move in the sky. And so by shifting each image as you stack it at a certain rate, you can actually find these like point-like sources. So that's kind of something we work on to find new Kuiper Belt objects. So that's what the process I know about that. If you have any further questions about that, let me know, but that's kind of the thought process behind that. It's pretty complicated overall. Yeah.
This is a really interesting question, Michelle. I'm going to touch on it a little bit, but I think other people might be more qualified to answer it. So you're asking if certain celestial objects need to be observed at certain wavelengths. That actually depends on the type of information you want to receive from it. If you're doing high energy astrophysics, like if you're observing a quasar or something like that, then maybe you want to use X-ray. Maybe you want to write a proposal for the Chandra telescope or use a data set like that. If you're observing like neutron stars colliding, maybe you want the gravitational wave data, or maybe you also want the electromagnetic data. As far as, like the Hubble data set I'm working with, I'm using visible, just optical wavelengths, which are fine. And you don't really need a book to tell you what that is. You can just Google what are optical wavelengths. And then that could tell you what filters on a telescope might be in those wavelengths. But maybe you want infrared. Maybe, not being able to see through dust is a really big problem. So then you need waves that are going to be able to get you to see through some of that stuff. So maybe you would want infrared or some other different wavelengths like that. So I would say there isn't really a wrong answer. It just depends on what information you want for this specific study.
And yeah, you can find that all on, they should all be online. There are some very common like filters used in astronomy that you'll likely be using. And you can find like the exact wavelength ranges and all that on. So yeah, like I I wouldn't worry about, I don't know which filter to use. Because again, like assuming you're using existing data out there, like they'll be sure to like label like this was taken with this filter. And then you can just search like what that corresponds to in wavelengths.
Yeah, so how to get telescope time is kind of a big deal in astronomy. So kind of overall what you do is these telescopes have boards of people who decide who deserves to have time and who doesn't. And you submit a proposal, so you just explain what you want to look at, what your scientific objectives are, and kind of justify also why you want to use that telescope specifically for your purposes. And then you have to, calculate the time it's going to take, all that sort of thing, to so they know like what exactly you're requesting of them. And then these committees will decide how to allocate that time, and hopefully your proposal is selected as one that gets observing. So someone with more like HST experience can chime in, but I know that the James Webb Space Telescope proposals were recently due, and that's kind of a similar process for that, but it's kind of like the same process overall. So if someone wants to chime in about HST specifically.
Yeah, so I don't really have a lot to add on HST specifically. I just know that Professor Bell recently wrote a proposal for them. But just to piggyback off of what Anna was saying there, applying for telescope time is almost like applying to college, where when you apply to college, you have to write all these like essays on the Common App, and it's, a lot of work. And, I guess in college, they look at your grades and other stuff. You don't have to do that when applying for a telescope, but you almost have to write a pre-paper, a proposal where you have very specific goals on what you're trying to find, the methods you're going to use to find it, and what you like anticipate results to be, and why you think that's going to be significant or not significant. And you can't just say, I'm interested in stellar halos, so I want to look at NGC 253, and I just need an hour of time. They're going to say, how long is the, ACS F606W filter going to need to be turned at this angle looking at this galaxy? Like, you need to be incredibly specific with exactly what you want everything to be doing and how long it's going to take for them, because they're going to have a bunch of other proposals where people have specified that information. And especially for stuff like HST, James Webb, all of that, many people, many institutions are going to be applying for those grants, and there's really no guarantee that you'll get the grant if you apply for it. So I just want to emphasize, it's actually really, really hard to write a proposal and to get that observing time. And moreover, you even if you get the observing time, it might not be the same amount of time that you wanted to get. They might give you less because they prioritized other studies.
Yeah, I can jump off of this as well. This also applies not only for those space-based telescopes like Chandra, Hubble, and JWST. The same thing applies for ground-based telescopes. Usually what happens is that any institution that has stake in that telescope or observatory has pre-allocated time to that telescope or observatory, and then the rest is divvied up by anyone that submits an application. One of the jobs that you can have in astronomy is to be the person that runs the telescope. It's too expensive for each individual person that submits an application to go and be involved when it's their time to view their objects. So they're all sent in once the time allocation committee decides what objects are going to get time. That gets sent to what is called the Q observer, and they're the ones that are actually at the observatory and picking the objects and whatnot. Another reason that they use that method is that if you go in person and say for a weather reason you're not able to open up the telescope, or that you run into light pollution issues, or the moon is too far, or anything like that, you don't get those days back. If you lose out any time, it's just too bad. So that's one of the reasons that they use this allocation style, is that the person that is there all the time has more ability to be flexible with the objects that they're observing on certain nights, and are better able to make sure that the most objects can be viewed as possible, rather than having each person come individually and trying to view their objects, and each one running the risk that they're not going to get enough time in order to view other objects.
Michelle, yeah, I use JPL Horizons all the time. So yeah, for solar system objects, yeah, that's definitely a tool to be used to get that. And yeah, it's great that you know about that because it's a really cool resource. But that is one of the things we use to get info about solar system objects. So yeah.
Yeah, I just want to emphasize, these are really, really good questions, by the way. I can definitely tell that like you put a little bit of thought behind these. So we definitely really appreciate everybody's questions.
Although I will say the issue with JPL Horizons is that you do not know, it only has things that are known objects with good orbits, right? So if you are looking for new objects, they're not going to be in there. So that's kind of its limitations, of course, but.
All right. Do we